Hi there. Welcome to lecture 18 of Fox, where we're going to be talking about random variables, which is a concept that allows us to take a complex experiment and focus on what we are interested in from the experiment. Okay. But let's have a quick recap of what we did last time. So we talked about independence and how we can use independence to estimate complex probabilities by breaking down the complex event into an AND of several events, and then independence allows us to compute the probability as a product. Okay. Then we talked about coincidence and various paradoxes that arise, because of coincidences, but they're not really paradoxes because when you sit down and compute the probability, well, you get the probabilities that you expect. Okay, and we showed an application of this analysis of coincidences, Fox twins, the birthday paradox, to hashing, a very important algorithm in computer science. And lastly, we talked about random walks and the gambler's ruin problem. So random walks are also another very popular type of process that you might encounter in practice. Okay, what are we going to do today? Today we're going to introduce this very important concept of a random variable. A random variable allows us to, handle complex experiments, complex outcomes, and allows us to focus on what we are interested in from that experiment. Okay, and associated with a random variable is a probability distribution function, or PDF. Okay, and it's a very similar concept to a sample space and the probabilities associated with the outcomes. Okay, so it's not a huge leap from what we already know. And we'll spend most of our time, studying four very important random variables that are very important in computer science and just very important in general: the Bernoulli, the uniform, the binomial, and the exponential. So these are four very important random variables. So we'll introduce them, spend a little bit of time, and that'll take us to the end of the lecture. Okay, so let's begin. Let's go to the board. So what is a random variable? Okay, so let's start huge, okay, but then we're going to get very small and very simple very quickly. Okay, so let's think about all the molecules of air, in this room. Okay, and each molecule has a random position and a random velocity. So it's somewhere and it's moving in some random direction. Okay, now are we really interested in an outcome for all these randomly positioned and randomly moving molecules? So how would I specify such an outcome? Okay, I would have to tell you for all the 10 to the 24 or so molecules in this room, I'd have to tell you what's their position and what's their velocity. And that would be an outcome. Okay, for this experiment which randomly, places and all the molecules in the room and gives them some random velocity. That's what I would have to tell you. It's a very, very, very complex outcome. Okay, and there are many different outcomes that you could imagine, and we call each specific outcome a realization or an outcome of the experiment. But are we really interested in all the various positions and velocities of all the molecules? No. So we're not really interested in the actual outcome of this random experiment. Okay. What are we really interested in? What we're really interested in, so let's say we're an experimentalist or a physicist or something like that, what we're really interested in is some macroscopic property of, the air in the room. For example, the temperature. Okay. And what's the temperature? Well, the temperature is defined by the positions and velocities. So it's some function of all the positions and velocities, i.e. it is some function of, the outcome, the random outcome. Okay. So at a high level, you can think of, you do an experiment, there's this very complicated outcome. Okay. And now you take a measurement of some property about this outcome, such as the temperature in the room. Okay, and that is exactly what a random variable is. It's a measurement that is taken for the outcome that results from an experiment that involves randomness. So you do an experiment, you get a complex outcome, but you take a measurement like the temperature. Okay, so now let's get very, very simple. Okay, and let's talk about coins. Let's toss 3 coins. Okay, and for example, if we toss 3 coins, we might get the outcome H, H, T. So this is a complex outcome. Complex outcome. Okay. And if you tossed 100 coins, you'd get some even more complex outcome. H, 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 T, H, T, H, T, 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 H, 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 and so on. Okay. So you have some complex outcome of 100 tosses. But very often, we're not interested in the specific outcome, just like we're not interested in every position and velocity of every molecule in the room. We're typically just interested in some property of that whole sequence, some measurement that we take of that whole sequence. So, for example, we might be interested in the number of heads, so we can measure the number of heads in the outcome. Okay, so number of heads for HHT, for the outcome HHT, is 2. Okay. Another kind of outcome, another kind of measurement that we'd like to do is, we'd like to measure and see, do all the coins match? Okay, do all the 3 flips match? Okay, matching, let's say, is another measurement. Okay, so matching of HHT is no, it doesn't match. So we might say 0. Okay, so this is the number of heads. Okay, this is a very special kind of measurement. It's just asking, does the outcome have some property, yes or no? We call that kind of a measurement a binary measurement or an indicator measurement. Okay, so this is an example. This indicates, quote unquote, if all coins match. Okay. Now, let's look at all the possible outcomes. Okay, so, while I said that, we are, interested in very complicated experiments, and usually we're not interested in all this, in the entire outcome and all the outcomes. Okay, let's just, for the moment, analyze in this example all the possible outcomes when we toss 3 coins. Okay, so all outcomes, remember we call that the sample space omega. Okay, so this is all the outcomes, and let me list them out in a systematic way. HHH, as usual. HHT, HTH, HTT, THH, THT, TTH, TTT. Okay, so I listed all the outcomes. And we've done this probability space many times already. Okay, so, so I'm extending this table. You'll see why soon. We've done this probability space many times before. So we have the probabilities for the outcomes. It's a uniform probability space. So it's 1/8, 1/8, 1/8, 1/8, 1/8, 1/8, 1/8, 1/8. Okay, good. And now let's see what our measurements produce for each possible outcome. So let's talk about the number of heads. That's a measurement, so important. Think of it as a measurement for the complex outcome, okay? And it summarizes the outcome, to the quantity, the thing, whatever it is that we are interested in. So it's a summary of the outcome, a measurement of the outcome, okay? And, let's call that measurement X. So these are the outcomes omega. So these are the outcomes omega. These are the probabilities. Okay. And now I'm going to call the number of heads X. Okay. Okay. And let's see what the number of heads are. Well, in this case it's 3. In this case it's 2. In this case it's 2, 1, 2, 1, 1, 0. Okay. Now, what you will observe is I've assigned to every outcome a number of heads. And so that's important. To every outcome of my experiment, my random experiment of tossing 3 coins, I have assigned a measurement. I can take this measurement for every outcome. In other words, I have assigned a number that corresponds to this measurement to every outcome omega. What have I done? I have defined a function. It's a function. And if you tell me the input omega, I tell you the measurement X. So I could write this as, this measurement that I'm doing is essentially a function. Okay, it's a function that takes as input omega and outputs a value, which corresponds to my measurement. And the measurement I'm interested in here is the number of heads. Okay, I could be interested in another measurement, which is, do the coins match? So I could call that measurement Y. Okay, and it takes as input the outcome. Okay, and tells me 0 if they don't match, 1 if they match. So, let's see what this measurement Y looks like. The measurement Y is yes, they all match. No, 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 yes. Okay, so this is the number of heads. This is the number of matching indicator. Okay, and the thing I want to emphasize, is that nothing complicated going on here. I'm just taking a measurement of the complex outcome, and this measurement I'm calling X, and this measurement I'm calling Y. But the important thing to observe is that I can take the measurement for any outcome. So essentially, I'm defining a function, that maps outcomes to numbers. The number is the measurement, number of heads or 0 or 1. Okay, and this concept of a measurement is what we call a random variable. And now I'm going to give you the abstract definition of a random variable. Sorry, random variable. Okay, there's nothing random about a random variable. It's not even a variable. And you'll see the definition of a random variable is very simple. It is a function. So let me, for example, think, and we typically call the random variable by big bold letters like x and y. So for example, the random variable x is a function, okay, which maps your sample space omega to the real numbers, i.e. a measurement, to a measurement. And usually the measurement is a number, okay? And so we call those real valued random variables. But you could measure other things. You could measure, you could map a complex outcome to a matrix. That would be what's called a matrix valued random variable. You can have complex valued random variables and so on and so forth, okay? But in this class, we're just going to be interested in real measurements, things that you can measure from an experiment. So a function which maps the sample space omega to a measurement x, okay, and that which maps, let me say, okay, which maps an outcome omega to a measurement x of omega. In other words, for every complex outcome of your experiment, you do the measurement and get a value, like temperature or number of heads. Okay? And sometimes we write that if we wanted to show off our mathematical strength, we would say that the random variable x is a function which maps your sample space to the real numbers. Okay, so that's all that a random variable is. That's all it does. Okay, that's all it does. Intuitively think. I do an experiment, I get a complex outcome, I take a measurement. That measurement is a random variable. Mathematically, when I do an experiment, okay, abstractly, I have a sample space of all possible outcomes, and a random variable simply maps the sample space to numbers. Okay? Now, in this case, we defined two random variables. So there's nothing wrong. You can have any number of random variables. It's like taking the temperature and the pressure of the gas in the room. So you can take multiple measurements if you want. That just corresponds to, multiple random variables. No problem. So here, we're taking one measurement, which is counting the number of heads, and another measurement, which is 0 or 1, depending on whether they match, indicator. Okay, that's also fine. No problem. Okay. The interesting thing about a random variable is that we can use it to define events. Okay? So we could ask, for example, what is the probability that my random variable x is equal to 2? Okay? And we analyze this in exactly the same old fashion. Okay? Well, this is, stating, it's a question. We're asking a question. What are the chances that for example, what are the chances that in this room the temperature is above, 75 Fahrenheit? So what are the chances when I toss 3 coins, I find exactly 2 heads? So we identify the event of interest, the subset of outcomes that correspond to the measurement 2. Okay, so what is this? This is the probability of where do we get a 2? 1, 2, 3. So that's the probability that the outcome is in the set. The event of interest is HHT, HTH, and THH. Okay, so that's all it is. Okay, so we can use a random variable to define events, and this is 3/8. Okay, just add up, 1/8, 1/8, 1/8. Okay, we can say, what's the probability? Quick exercise. What's the probability that x greater equal to 2? Okay, so go for it. Let's see if you can compute this value. I'll pause the video. Okay, I'll give it a few seconds. 1, 2, 3, 4. If you're just coming back for the ride, or you answered that the probability that x greater equal to 2 is equal to 1/2, you are correct, because let's identify the outcomes. It's the probability of the outcomes. So greater equal to 2 is 1, 2, 3, 4. H, 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 T, H, T, H, T, H, T, H, H. Okay, it's a 1/2. Okay, what about the probability that y is equal to 1? Okay, what's the probability that y is equal to 1? Okay, so you have to identify the outcomes, okay, and tell me what's the probability. So if I'll give you a couple of seconds, pause the video. Okay, now 1, 2, 3. If you're coming back and you said the probability is 1/8, fantastic. You're on, 1/4, fantastic. 1/4, fantastic. Okay, so how do we get 1/4? Well, we identify the outcomes where y is 1, 2 outcomes. So add up the probabilities, 1/8 plus 1/8, 2/8 is 1/4. Okay, now, complicated. What about the probability that x equals 2 and? So I'll just say comma, okay, for the and, to imply and. So x equals 2 and x greater equal to 2 and y equals 1. Okay, what's the probability of that? So pause the video and work it out. 1, 2, 3, 4, 5. Okay, so let's look at the events. So x has to be greater equal to 2. So we've narrowed the outcomes to this, and this. And now, and we want y equals 1. So we've narrowed the outcome to this. So this is the only outcome where y equals 1 and x greater equal to 2. And so if you said 1/8, bam. Okay, you have understood how to construct events from random variables and then compute the probability. Okay, fantastic. Okay, so let me tell you about the probability distribution function. Okay, so the probability distribution function, or PDF. Okay, so let's look a little more closely at what a random variable manages to accomplish. Okay, so we had 8 outcomes, so complex outcomes. And the random variable took each outcome and just reduced it to a number, a measurement. Okay, so effectively what a random variable did, in this example, for instance, is to take my entire sample space and map it to a bunch of numbers, in this case 0, 1, 2, or 3. Okay, so we had a whole sample space, okay, omega, okay, so which was, H, 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 T, H, H, T, H, T, H, T, H, H, T, 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 H, H, T, H, T, 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 H, T, T, T. Okay, so this was omega. Okay, and our random variable x mapped this entire complex set of outcomes. Now, if we had, this is just 3 coins. Imagine if we had 20 coins, okay? So the number of possible outcomes is 2 to the 20, which is, more than 1 million, okay? So it took this complex sample space and mapped it to the very simple space of measurements, the very simple set of measurements, 0, 1, 2, or 3, okay? So that's what our random variable x did. A function that maps one set, the sample space, into another set, the set of possible measurements. So we call this set, let's call this set x of omega. It's the set of possible measurements. So what happens when you take a function and apply it to the whole space? What are the possible values of x? Okay, so the set of possible measurements. Okay, that's the set of possible measurements. Okay, so we can use, and now we just saw that we can use the random variable to define an event. So we can define the most basic kind of events. So what is the probability that my random variable takes on a particular value? Okay, so we can talk about what's the probability that my random variable x equals 0, the probability that x equals 1, the probability that x equals 2, and the probability that x equals 3. Okay. Well, the most basic events that can be defined with respect to my random variable. In other words, take all the possible values of my measurement and ask what are the probabilities for each possible measurement. So let's put that in a table. Okay. So, if I put here x of omega, so the set of possible measurements, okay, the possible values for my random variable are 0, 1, 2, and 3. Okay, and now we can ask what's the probability of each. So we call that, when we talk about the probability of each possible value of my random variable, we call that the probability distribution function for my random variable. Okay. Now, the set of possible measurements, because we call this guy big X, we will denote by little x. So these are the little x. So we'll denote by little x. Okay. And so now we can ask, what's the probability for each possible value of little x? And sometimes we sort of emphasize that these are the probabilities for the random variable big X. So we might write P sub big X of little x. So little x is just taking on the various values, 0, 1, 2, or 3. And so we're asking, what's the probability of each value of the measurement? What's the probability for each value of little x? So what are the chances that you get 0 heads in this example? Okay, 0 heads, it's 1/8. Okay, 1 head, well, what's the event? The event is this guy, and this guy. So there are 3 outcomes, so that's 3/8. Okay, 2 heads, that's this guy, so 3/8. And 3 heads, it's just this guy, 1/8. Okay, and this set of probabilities for the corresponding little x value, this is called the probability distribution function, PDF, the probability distribution function of x. Okay, good. Now, certainly we can list the PDF as a table, but very often we like to plot it as a bar chart or even just a regular chart. So let me show you what that would look like. So what we do is we plot, all on the x-axis, all the possible values of x. So we have 0, let me put 0, 1, 2, 3. Okay, so those are the possible values of x. And now we have here 1/8, 2/8, 3/8, and we can keep going if we had, more likely possible values of x. And now 0 has a probability 1/8. So get a bar for 0. Then we get a bar for 1. The probability of 1 is 3/8. And 2 is also 3/8. And 3 is 1/8. So that bar graph, this bar chart, represents the PDF in a nice visual way. Okay? And so we will equally call this the probability distribution function for the random variable x. It tells you for every possible value of the random variable, okay, what are the chances, what are the probabilities. Now, an interesting thing has happened. What has happened here is we had our original sample space, the original outcomes that could happen in our experiment. Okay? And then we took a measurement, and we can take more than one measurement if we want. Okay, so we took a measurement x, okay, and that transformed our sample space to a much smaller, simpler space that we can handle. Okay, and so the possible outcomes become possible measurements, possible values for the random variable x. Okay, and associated with each possible value for the random variable x is a probability. Okay, and in some sense, we can now focus on this probability distribution function as the essential summary of the experiment with respect to what we are interested in. We are interested in the number of heads, or in the temperature, if we're looking at a physical system. So we are interested in the number of heads, and the only thing that we care about is what are the possible values of heads, and what are the probabilities for each possible value. So in some sense, we've sort of, created a condensed new sample space, the possible values of x, and and associated with these new outcomes in some sense, but these are just the outcomes that we are interested in, the property of the actual complex outcome, okay, the property, the measurement that we are interested in, and the corresponding probability. So this is just like a new sample space and probabilities corresponding to that new sample space. Okay, and we can also define events with respect to this new sample space. So we could ask, what are the chances? What's the probability that x is greater or equal to 2? Okay, so we just look here. What's the event that's associated with that? 2 greater or equal to 2 is, this outcome and that outcome. So we have, two outcomes for the measurement x, and their probability is 3/8 and 1/8. So we get 3/8 plus 1/8 equals 1/2. Exactly the same thing that we got by working from the original sample space. Okay? But this is much more convenient. we can now compute probabilities of events that involve only the measurement x using the PDF for x, or this new, in some sense, simplified probability space. Okay, so while the true outcomes and the true sample space exist, as far as we are concerned, now they take a background seat. And what we are really interested in is the measurements that could occur, the possible values, and what are their probabilities. That's all we care about. And typically, this is what we do. We now forget about the sample space, the original experiment and the corresponding complex outcomes, and focus on the measurements and their corresponding probabilities, and define events with respect to just measurements. Okay? And it simplifies things a lot, because we don't need to work with complex sample spaces anymore. We work with the simplified measurement space and the associated probabilities. And that works as long as we only need to define and analyze events that can be defined using the measurement. So, for example, x greater equal to 2. If we wanted to know what are the chances that, you got x, what are the chances that, you got more than two or more heads, and the first flip was a heads, well, this doesn't contain that information. Then you have to go back to the original sample space. Okay. All right. Let's do one more quick example. Okay. And then we will move on to some very important random variables, measurements for complex experiments. Okay. So one more quick example. Let's do another quick example. Dice. Okay. So let's roll a pair of dice. Let's roll a pair of dice. Okay, and if we roll a pair of dice, what are the possible outcomes? So we did this last time. Die 1 can have either 1, 2, 3, 4, 5, 6. Those are the possible rolls of die 1. And die 2 can roll 1, 2, 3, 4, 5, 6. Okay, so I'll put dots. Remember my dot drawing mechanisms. Let's see how good I am at drawing dots. Wow. Boom, 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 boom. Boom, 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 boom. Boom, 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 boom. Boom, boom, boom. Boom, boom, boom. Okay, so those are the possible outcomes. This is die 1. 1, 2, 3, 4, 5, 6. And die 2, 1, 2, 3, 4, 5, 6. Okay, and now, yes, complicated. 36 possible outcomes. And it's a uniform probability space, so each of these has probability 1 over 36. Okay, and we may ask, what are we interested in when we roll a pair of dice? And that's the measurement. Okay, and so let's say we're only interested in the sum. Okay, so then random variable x is equal to the sum of d1 and d2. Basically, it's d1 plus d2. Okay, you could be interested in the difference, you could be interested in the product, whatever. Okay, but we are currently interested in the sum. Okay, so what are the possible values of the sum? So let's see so the original sample space is this. What are the possible values of the sum? What is x of omega? Well, if the minimum value is 1 plus 1 is 2, and the maximum value is 6 plus 6 is 12. So the possible values are, no surprise, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So those are the possible values. Okay? And now we can construct the probability distribution function for the sum of a pair of dice, okay, by asking, what is the probability that you roll a 2? What is the probability that the measurement is a 3, 4, 5, and so on? So let's see. You're rolling a 2, that's just this guy. Okay? That's just this guy. Okay? Rolling a 3 is 2, 1, or 1, 2, so that's this guy. Okay, rolling that's 3. 4 is 3, 1, 2, 2, 3, 1, 3. So that's just this guy. Okay, rolling this is 4, this is 5, this is the sum 5, sum 6, sum 7, 8, 9, 10, 11, and 12. Okay, so those are the events. So let me label them. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And now to compute the probability, so we can say this is P sub x of little x being the measurement. Okay, well, there's only one outcome which satisfies the sum is 2, so that's 1 over 36. And you'll see for the sum being 3, there's 2 over 36. Okay, 3 over 36, that's 3. 4 over 36, 5 over 36, okay, and then 6 over 36, and then 5 over 36. Now it starts going back down. And then 4 over 36, 3 over 36, 2 over 36, 1 over 36. Bam! And that's the probability distribution function for the sum of two dice. And we can plot it in that bar chart if we wanted to. So let's just do that for completeness. Okay, so as a bar chart, the possible values are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And you have 1 over 36, 2, 3, 4, 5, 6. 6 is the max. So 2 over 36, 3 over 36, 4 over 36, 5 over 36, 6 over 36. Okay, and we'll just do it. So the sum of 2, sum of 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's the probability distribution function for the sum of a pair of two dice. And you can easily see from here or the table that the most likely outcome is 7. Okay, so the most likely sum is 7. Okay, now I just want to mention a couple of things, and then we'll go on to these very popular, very important, very common random variables. So experiments and their associated measurements that we are interested in. Okay, so the cumulative distribution function. The cumulative distribution function. Okay, so this is related to the PDF. Okay, and you can read all about it in the text. And basically, the PDF asks the question, what's the probability that x is equal to, let's say, 2? The CDF captures the probability that x is less equal to 2. So as opposed to equal to, less equal to. Okay, so that's another common way of analyzing a random variable x is through the CDF, and you can read about it in the text. What I want to talk about, at least a little bit, is the concept that you may have more than one random variable. Okay, so here we have in the same experiment, we have the number of heads and the indicator of whether the coins match. Okay, so you can have more than one random variable. So you can have more than one random variable. There's no harm in that. There's nothing wrong with that. And so you can analyze, complex events like, what's the probability that something is happening with one of the random variables and another random variable. Okay. Now the typical way we condense the entire outcome space when you have more than one random variables defined for the same experiment is using what's called the joint probability distribution. So this leads to the joint probability distribution function. Okay, that's called the joint PDF. So again, I'm going to ask you to read the text for that. I'm not going to spend so much time on that. Okay. What I would like to talk about is what about when you have the random variables from different outcomes that are completely independent. So let me give you an example. Okay. So independent random variables. Okay. So let's say you toss 5 coins. Toss 5 coins. Okay. And then independently, okay, you toss another independent 5 coins. Toss another independent 5 coins. Okay, so now we can measure for each of these experiments, so independent experiments, and this is typically the way we will encounter multiple random variables. Okay, but for sort of independent experiments, you've got, you can measure the number of heads in the first 5 coins, so let's call that x. Okay, the number of heads in the first 5 coins. Excuse me. Okay? But you can do the same thing for the second 5 coins. Or you might not measure the number of heads. You might measure whether or not all the 5 coins match. You may make some other measurement. But for the, whatever it is, we could call it a random variable y. Okay? And for simplicity, let's imagine that we measure the number of heads in the other experiment. Okay? And now we can ask, what is the probability that x equals little x and y equals little y? Okay, so for example, what is the probability that x equals 3 and y equals 2? Okay, and you see this is related to a joint probability distribution function, but we're talking about the special case where the experiments are in some sense independent. So what we say is that these random variables are also independent in such a situation. Okay, and the probability of something happening with random variable x and a totally independent random variable y, it's exactly what we would expect. It's the product. Okay, so this is going to equal the product that x equals x and y equals y. And this is the PDF for x. And this is the PDF for y. Okay, and we say that these random variables x and y, the random variables x and y are independent. Okay? And it's because we can compute the probability of an and using a product. And that's especially the case when the experiments are totally independent, like here. Now, you can define independence even for the general case where, the random variables make measurements on the same sample space, and that's where the joint probability distribution function comes in, and so on and so forth, okay? So read all about that in the text. But for our purposes, whenever we encounter independent random variables, it's usually because those random variables are measurements in totally different, totally independent experiments. Okay, so what have we talked about so far? Well, we've introduced the concept of a random variable. Don't panic. It's just a measurement. You run a complex experiment, you get a complex outcome, you take a measurement, you get a value. Okay, and so a random variable is effectively just a function that maps outcomes, complex outcomes, to values, i.e. measurements. Okay, it's just a function that maps a set of outcomes to a set of numbers. Okay, and now once you view it that way, then the set of possible outcomes, so the set of possible values for the random variable becomes your new effective sample space, and the associated probabilities become what's called the probability distribution function for the random variable, and so the random variable and its associated probability distribution function summarize the experiment with respect to what we are interested in. So we can focus on what we are interested in, which is the measurement. And usually at that point, we can now forget about the sample space, which is complex, and focus on the possible measurements and their probabilities, or the PDF for the random variable. Okay? And that's the value of the random variable. It summarizes a complex experiment into the simpler PDF that we are interested in. And then we talked about, the possibilities where you have multiple experiments and multiple random variables coming from each experiment, multiple measurements from each experiment. Okay? And the fact that if the experiments are independent, then the random variables are also independent, and you can compute probabilities of and by just multiplying probabilities. Okay? Now, let's go and talk about all kinds of different random variables. So we will do the usual. Speed erase. There. We are now going to study some common random variables that are likely to occur when you do an experiment and take a measurement. Okay, so these are the types of measurements that we, usually take. Okay, and so let's start with the simplest kind of measurement of all, the binary measurement. Just like we discussed, are all the tossers matching? So that kind of binary measurement, yes, no, 0, 1, left, right, up, down. Okay, so anytime the measurement you take can have just one of two values, okay? We call that a Bernoulli or binary random variable. So Bernoulli or binary random variable. Okay, so the idea here is that, remember, when you've done the experiment, you've obtained the random outcome, you take your measurement, okay, and now we analyze the various probabilities of the various measurements, i.e. the PDF. Then we can forget about, the details of the experiment and the complex outcomes. We can focus on the possible values of the measurement and their probabilities. So we can focus on the PDF. And so when we talk about random variables, we're just going to focus on the possible values of the random variable and its PDF. Okay. And that basically, tells you everything you need to know about the random variable. Okay. And so the Bernoulli random variable, there are just two outcomes. Okay. So let's call it X. Okay. So the outcome can either be 0 or 1. Okay. And so this is the Bernoulli random variable. And we typically assign the probability of 1 to be P. Okay. And since these are all the possible outcomes, the probability of 0 then becomes 1 minus P, because some measurement, either 0 or 1, has to occur. So if the probability is P for 1, then the probability is 1 minus P for 0. And if I wanted to put it in a table, the possible X values are 0 and 1, and the probability of X, and if I wanted to be completely formal, I would say P sub big X of little x is 1 minus P and P. So that's the Bernoulli random variable. And you think, wow, really? Yes, anytime you're interested in an indicator. Will it be sunny or not tomorrow? Bernoulli random variable. So you do your complex, weather simulation. It has randomness in it, and it gives you an outcome. And then you measure whether or not it'll be sunny. So a Bernoulli outcome is on its own a very, important outcome. But very often in practice, we are interested in more complex measurements, and those complex measurements can involve, a sum of Bernoullis. So let's take a couple of examples. Okay, so sums of Bernoullis. Okay, and the simplest example of a sum of Bernoullis is you flip a coin n times, or you flip n independent coins. Flip n independent coins. Okay, how many heads did you get? That X equals the number of heads. So that's a measurement. Okay, but now we can imagine flipping each coin, as a separate experiment. So flip each coin as a separate experiment. So, you have maybe heads, tails, heads, tails, and so on. So each coin is a separate measurement, and we will typically indicate by, typically indicate, a Bernoulli random variable as indicating success or failure. Okay, so success probability P, failure probability 0. Okay, and in this case, we can say that you succeed if you get a head. So you're looking for a head. So this is a succeed. So this is, this is a Bernoulli, and it was 1, and this is a Bernoulli, and it was 0, and it was 0, and this was 1, and this was 0, and so on. Okay, so flipping a coin or flipping n coins corresponds to, n independent Bernoulli outcomes. Okay, and that's how we would typically even refer to this. We have n independent Bernoulli outcomes. Each of them is a Bernoulli random variable, either 1 or 0. And the thing that we are interested in, the measurement, is just the sum of these, because the sum of these is equal to the number of heads, because you get a 1 for each head and a 0 for each tail. So this is just the sum of the individual Bernoulli random variables, of the individual Bernoullis. And there's no problem. So effectively what we're saying is we've defined a random variable X in terms of using other random variables, okay, x1 plus x2 plus x3 plus x4 plus all the way to xn if you tossed n coins. Okay, so what we're saying here is a random variable X is a sum of other random variables. This is called a sum of Bernoullis. It's a very important random variable. Okay. We will see later when we discuss the binomial. This is exactly what a binomial random variable is. Okay, so this is an example of using one set of random variables to define another. So these each take a value in 0 to 1. So this takes a value in that can be either 0, 1, 2, or and so on up to n. Okay. All right, so that's the Bernoulli random variable, and we can, it's important on its own, because a lot of times we're interested in, a binary outcome, but also it's important because we can build other random variables as a sum of Bernoullis, and that also happens often. Okay, let's talk about the uniform random variable. This is the other kind of simplest possible random variable, the uniform random variable. Okay, so it's a measurement that takes on some values, okay, and each value is equally likely. So the measurement takes on some values, and each value is equally likely. Okay, so sometimes we just list the values. So uniform random variable, let's call it U. Okay, sometimes we just, a uniform random variable on the interval of numbers 1 to n. Okay, basically can equal one of these numbers. So the possible values are 1, 2, 3, 4, let's call it k, up to k. Okay. And because it takes the same probability on each of those, the probability is 1 over k for each possible value. Okay. So these are the possible values for the uniform random variable, and these are the probabilities. Okay, so it's a very simple. If you look at the PDF, so for the possible values 1, 2, 3, and so on up to k, it's just a constant. Okay, so if I were to draw the PDF, it would just be a constant, 1 over k, and it's just a constant. That's what it looks like. Okay, now, if you have a Bernoulli random variable and the probability of success is 1/2, then the probability of failure is 1/2, and the Bernoulli becomes an example of a uniform random variable. Okay. In general, uniform random variables, can occur. Okay, it's rare that they typically occur in practice. Usually we use uniform random variables when we develop algorithms. So I'll give you some examples of that. Okay. When I was young, so Malik lived at home. Okay. And this is school. So Malik goes to school. Okay. And, there were two paths to school. So there was the first path and a second path. Okay. And I've drawn, the paths with colors, but the colors don't really mean anything. So I have to choose a path to go on, and I had this great friend, let me call him the Grim Reaper. So I had a great friend called the Grim Reaper. Okay, and, the Grim Reaper would, if the Grim Reaper met me along my path, usually I was relieved of my lunch and what used to be called my pocket money. Okay, and so I would always want to try to pick a path that, would avoid the Grim Reaper, but somehow the Grim Reaper always knew which path Malik was taking to school. Okay. And so, if Malik had known probability, then it turns out that Malik could have won half the battles with the Grim Reaper. So Malik could win half the battles with the Grim Reaper. By avoidance, basically. What would Malik do? Okay, so it turns out that, if I had a coin, so a uniform random variable with two outcomes, heads and tails, half, okay, I flip the coin, and only based on the coin, I will decide which path to take when I get to my choice. Okay, when I get to the point where I need to make the choice, I flip the coin. Now, no matter what Grim Reaper's strategy is, okay, Malik will win half the battles just by avoidance. Okay, by avoidance. So that's an example of how we use uniform random variables in practice when we develop algorithms. So uniform random variables, they might not occur too often in practice. Now, one of the cases where they will occur in practice is, you roll a die, okay? And if it's a fair dice, then the outcomes are 1, 2, 3, 4, 5, 6, and the probabilities are 1, 6 for all. So that's a uniform random variable. But once you get a little more sophisticated and roll 2 dice and are interested in the sum, it's no longer a uniform random variable. We saw the sum of 2 dice just earlier. 2 is not very likely. The most likely number is 7, and then it comes back down to unlikely for 12. Okay? So even a pair of dice, the sum of a pair of dice as a random variable is not uniform. Okay. But uniform random variables are used a lot in algorithms. Let me give you another example of an algorithm where we can use a uniform random variable, and it might actually strike you as a little bit of a stunning example. Okay. So I encourage you to think about it. Okay. And I'm going to tell you, that a uniform random variable can be used to solve this problem, and it's a little bit miraculous that indeed it can be solved this way. So what's the problem? So it's a game between you and me. So there's Malik, okay, and student. Okay. And there are 5 numbers. So there are 5 numbers. 1, 2, 3, 4, 5. Okay. And what's going to happen is Malik is going to pick 2 numbers, any 2 numbers. So, and Malik gets to choose the 2 numbers. Okay, so here's how the game plays. Malik picks 2 numbers and puts them in envelopes. So for example, if Malik picks 2 and 4, he puts 2 and 4 in an envelope. Okay, sealed envelopes. Okay, and then what Malik is going to do is going to randomly jiggle these around, or it's basically flip a coin and randomly pick one of these. Okay, randomly pick 1. Randomly pick 1, randomly pick 1, and show it to you. For example, if I randomly picked 2, I would show you 2. Okay, so you will see 2. Now you have to guess whether the other envelope is larger or smaller. Okay, and you might think, well, since I'm randomly picking, how is it possible I'm going to have a 50-50 shot at winning this game? Because, you will equally likely show me either of these, okay? And so half the time you'll show me the larger one and half the time you'll show me the smaller one. And there's no way you showed me 2. I have no idea what the other one is. It could be 1 or it could be 3, 4, or 5, okay? And I'm not picking my 2 numbers randomly. I'm picking 2 numbers deliberately, 2 and 4, and I'm randomly shuffling them and then showing you 1. Okay, so you might think, okay, so one strategy might be, let me always say lower. So I'm always going to say that the number you showed me is the lower one. You'll be right half the time. Okay, if you always say, I'm going to say higher, you'll be right half the time. So the question is there a strategy that you can use? You have to tell me your strategy, whatever it is, so that'll influence what numbers I pick. But is there a strategy you can use which which allows you to win with probability strictly bigger than a half in this game? Okay. Probability greater than a half to win. Okay. So basically, I'm asking you to come up with an algorithm, a strategy, that will allow you to win strictly more than half the time. Okay. Now I'm going to tell you that any deterministic strategy you come up with, like always say lower, always say higher, all these strategies you can sit down and verify because I pick the number to show you randomly. Those deterministic strategies will all succeed with probability exactly a half. Okay, half the time, let's say you always say higher, half the time I'm showing you the lower number, so you'll fail half the time, because I randomly pick. Okay. But there is a strategy that gives you a success probability for this game more than a half. Okay. And you have to use randomness in the strategy. Okay. And in fact, you have to use it turns out that it's best to use a uniform random variable. Just like I use in my strategy a uniform random variable in order to avoid Grim Reaper. If you suitably use a uniform random variable in your strategy, you can win this game more than half the time. Just to show you, that, these days in computer science, we often use randomness, especially uniform random variables, in order to make the algorithms work better, with better properties. Okay. I'll show you another example of that today. Okay. So this is the uniform random variable. Now let's get on to the big ticket items. Okay, we're going to discuss the Bernoulli random variable and the exponential random variable. So let's erase. Okay, so the binomial random variable. The binomial random variable. Okay. Very important random variable. Okay. And this random variable occurs Okay, whenever you do something a certain fixed number of times, okay, let's say 5 times. So whenever you do something a certain fixed number of times, and each time you do it, it's independent. Okay, and each time you may succeed or fail. Okay, so let me state the sort of 3 basic conditions that come to play when we're talking about the binomial random variable. So 1, okay, you're repeatedly trying something some fixed number of times, a fixed number of times. Okay, so let's say say 5. Okay, and each time you try, you can either succeed or you can fail. Okay, so each time, each trial is a success or failure. Okay, and each trial succeeds with probability p. So the same probability p. Each trial is a success or failure, and in each case, the probability of success is p. So for example, p could be, let's say, 1/3. P equals 1/3. Who knows? So that means you're trying something over and over and over and over, a fixed number of times, let's say 5. Okay, and each time you will succeed with probability p. Okay, so it's important that each trial has the same success probability. Okay, and each trial, so condition number 3, each trial is independent. So you keep trying something and trying. Each trial is independent and succeeds with some probability p. And what you are interested in after you have done all your trials, okay, is, how many times did I succeed? So you're interested in the random variable x is equal to the total number of successes. Okay, very interesting. Okay. And you can see how this is very relevant to the real world, right? You get 50 shots at something, let's say shooting a bullet at a target, and each time you randomly try and you'll succeed in hitting the bullseye with, let's say, probability 1 in 10. Okay, so if you shoot 50 times, I'm interested in how many times did I hit the bullseye. Okay, so this is a very common thing, a very common experiment that we do in practice. You get a certain number of trials, and you try to succeed each time independently, and you have a success probability p. Okay, we're interested in the total number of successes. But now what's interesting here is that, each success or failure is a binary Bernoulli random variable with probability p. Okay, so the binomial random variable is exactly the sum of a bunch of Bernoulli binary random variables. Let us say that the fixed number of times you try, in this case 5, let us typically in general call it, n. So you have, a Bernoulli random variable x1 plus x2 plus x3 plus xn. Okay. So there are 2 parameters that are at play here. Okay, in this experiment. Okay, what are the 2 parameters? The first parameter is n, the number of trials I'm giving you. Okay, and the second parameter is p, the probability that you succeed in each trial. Now, let us consider the sort of prototypical, the simplest example, okay, the most common example of such a random variable, which is you just flip a coin, let's say 5 times. You flip 5 coins. Flip 5 coins. Okay, so let's see if it satisfies these 3 requirements. 1, you're trying something a fixed number of times. Yes, you have 5 trials. So 5 trials. Okay, are they independent? Yes. Okay, if the coins are independent. So we assume the coins are independent. Okay, 2. Okay, so 3, independent. Yes. Fixed number of trials? Yes. Okay. And is each trial going to succeed with the same probability? So we have to define success. So let's say success is a head. So is each trial going to succeed with the same probability? And that will be the case if they're identical coins. So typically we will say flip 5 identical coins. So then there's the same probability of success for each trial. Okay, so same probability of success. And P, okay, we'll call that probability of success P, and that P will equal a half if it's a fair coin. But in general, it can be a biased coin, or, in general, we will call it P. So for example, P might equal a third. Okay, so if you flip 5 identical coins, fixed number of times, they're independent identical coins, they're independent, and they all have the same probability of success. And the number of heads, so each of these trials is a Bernoulli random variable, x1, x2, x3, x4, x5. And what we're interested in is the total number of heads, which is the total number of successes. So we're interested in the total number of successes, which is x1 plus x2 plus x3 plus x plus x5. Okay. So let us compute the probability. So what's the random variable x, and what are its possible values? Its possible values are 0, 1, 2, 3, 4, 5. Okay, so these are the possible values. Okay, and let us now compute the probability for each possible value. Okay, and as an example, let's do, what is the probability of a total of 2 heads? Okay, so probability. Okay, so we need to look at all the various outcomes with 2 heads. Okay, so here's an outcome with 2 heads, H, H, T, T, T. Here's another outcome with 2 heads, T, T, H, T, H. Okay, so if we're doing the outcome tree for this experiment, what will happen? So you have your root, okay, and you could go either H, H, T, 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 or in this case you've gone T, T, H, T, H. Okay? So, and there are all the various other outcomes that give you 2 heads. But I just want to illustrate something with these 2 particular outcomes. And remember, these are complex outcomes. Ultimately, we want to just focus on the random variable, which is the total number of heads, which takes on the value 0, 1, 2, 3, 4, or 5. Okay. So let's put probabilities, for each of these edges. So this edge probability, if it was a fair coin, it would be half-half. But now I want to be general. I'm imagining, a probability of success P. And just to illustrate, let's use P equals a third. So we succeed with probability 1/3. So this is 2/3. Okay. This is 1/3, and this is 2/3. Okay. This is 2/3. This is 2/3, and this is 2/3. This is 1/3. This is 2/3, and this is 1/3. Okay, so now when I multiply the edge probabilities, I get 1/3, 1/3, 2/3, 2/3, 2/3. So I get 1/3 squared, 2/3 cubed. Okay. And here I get 2/3, 2/3, 2/3, 1/3, 1/3. So I get the same value, 1/3 squared, 2/3 cubed. That's very interesting. What if it was 1 instead of 1/3? What if it was some general number P, and this was 1 minus P? So then this would be P squared 1 minus P cubed, and this would be P squared 1 minus P cubed. Okay, and the thing to observe here is that, no matter how you arrange the heads and tails in this sequence, okay, no matter how you arrange them, when you look at that path in the outcome tree, you're going to have 3 1 minus P's and 2 P's. So all the sequences with 2 heads, okay, will have the same probability of 1/3 squared, 2/3 cubed, or more generally, P squared 1 minus P cubed. Okay, so let me write that down as a conclusion, a sort of reminder, very important conclusion. All sequences with 2 heads, in the tree have 2 edges, that are 1/3, and 3 that are 2/3. Okay, so the probability for that path, when you multiply the h probability, so the probability for that path is 1/3 squared, 2/3 cubed. And the squared has to do with the fact that there are 2 successors, 2 heads, and the cubed here has to do with the fact that there are 3 tails or 3 failures. Okay? And more generally, if it was not 1/3, it would be p squared and 1 minus p cubed. Okay. So then what's the probability of this event, that you have a total of 2 heads? Well, since each of the possible sequences has this probability, then to get the event, I need all those sequences, and then I add up the event probabilities. So when I add up the probabilities of all those sequences, I'm going to add this guy up for each sequence. So in other words, the probability of 2 heads, which is the probability of, which is the sum of the probabilities for each sequence with 2 heads, is exactly the number of such sequences times that probability. Okay? So now that's the important conclusion that we need. The probability of, x equals 2, okay, is equal to the probability to get a sequence with 2 heads, which is equal to the sum of probabilities for all sequences with 2 heads, okay, which is equal to the number of such sequences with 2 heads times 1/3 squared, 2/3 cubed. 1/3 squared, 2/3 cubed. Or more generally, it would be p squared, 1 minus p cubed. Who can tell me the number of sequences with 2 heads when the sequence length is 5? That's just the same as the number of binary sequences with 2 ones. This is just 5 choose 2. That is just 5 choose 2. Okay, so here I can plug in now. 5 choose 2. 5 choose 2. Okay, 1/3 squared, 2/3 cubed. Okay, so as a quick pop quiz, what am I going to plug in here? So what's the probability of 4 heads? Okay, so pause the video. 1, 2, 3, 4, 5 seconds. Okay, if you're coming back and you said 5 choose 4, okay, 1/3 to the 4th, 2/3 to the power 1, bam! You got it right. Okay. So each such sequence has 4 heads, so you're going to have, 4 heads in your outcome tree. So those each have probability 1/3 to the 4th, and then you have 1 tail, so that has probability 2/3, okay, to the 1. And the independence is crucial because that's what allows us to multiply probabilities for each of the individual coins. Okay, so now let's just give the general argument when you do this experiment in general and then do an example. Okay, so in general, you are going to try something n times, and the success probability is p. Okay, so let's make the same argument. Try n times, and success probability is p. Okay, you try n times and the success probability is p. And we are interested in, the probability that you get a total number of successes k. So the probability that the total number of successes, so this random variable x, which adds up the number of successes, the probability that the total number of successes is k. Okay. So let's look at one such sequence that has k successes. If we're, let's say, in the world of tossing coins, so it's going to have, so the simplest such sequence with k successes has the first k heads, and then the remaining k are tails. Okay, So there are k of these. And how many are there of these? And this is where the number of times you try becomes very important. How many are there of this? Is exactly n minus k. Okay. So now when you do the outcome tree, or you can just view it as from the point of view of independence, this happens with probability 1, p. This is p, this is p, this is p. So this is p times p times p times p. And then this is 1 minus p times 1 minus p times dot 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 times 1 minus p. Okay, so there are k p's, so we get p to the k. Okay, and there are n minus k, 1 minus p, so we get 1 minus p to the n minus k. Okay, so any sequence with k heads and n minus k tails has this probability. So the probability that x equals k has to add up the probabilities for all the possible sequences with k heads. But we know how many there are. There are n choose k sequences with k heads times the probability of those sequences with k heads, which is p to the k, 1 minus p to the n minus k. Okay, so this is the number of sequences with k heads, and this is the probability of one of those sequences. Okay. And so now we can fill in this table, okay, but we're going to fill it in for another example. Okay. So this is called the binomial distribution. This is called the binomial distribution. And this random variable is called the binomial random variable. Okay, and it satisfies these three conditions. Fixed number of trials. Each trial has a success probability p. The trials are independent. You are interested in the total number of successes. Okay, and we would like to know what's the probability of 0 successes, what's the probability of 1 success, 2 success, and so on. Okay. So I will rewrite that formula here now. The probability of k successes, which is the probability that x equals k, is exactly n choose k times p to the k times 1 minus p to the n minus k. Very important formula. And why is it a very important formula? It's because that process where you try something a fixed number of times and wait eagerly to see how many of them succeeded, that process is an experiment that we do very often in practice. Okay. Okay. So, let's do an example to show you how common this process is. An exam has 15 multiple choice questions. Okay, with 5 answers per question. 5 answers per question. Okay, so your strategy on this exam is to answer randomly. Okay, so you answer each question independently. So none of the answers in one question are going to influence whatever you do in the next question. So you answer the questions independently, okay, and you're going to answer randomly. So let's see. I claim that this is a binomial. So now you're interested, of course, in how many questions do you get right, okay, with this interesting strategy. And I know some students like to use the random strategy in my multiple choice tests. Okay, so I claim that the number of questions you get right is a binomial random variable. So let's see, does it satisfy these 3 conditions? Condition 1, you're trying something a fixed number of times. So yes, and how many times are you trying? 15 times. 15 trials. So n equals 15. Okay. 2, is the chance of success, in each trial the same? Yes. Why? Because you're trying each question independently and randomly, and you answer randomly. So, and since there are 5 answers, your chances of getting a question right are 1/5. So P equals 1/5. Oh, nice. Okay. And then, is each trial independent? Yes, that's the way you're choosing to approach this problem. Every question you're going to answer independently. So 3 independent trials. Okay, so given this, the probability that you get K right is equal to 15, choose K. Okay, 1/5 to the K times 1 minus 1/5, 1 minus 1/5, which is 4/5 to the 15 minus K. So let's see what that looks like. So let's draw the PDF for this random variable, random test answering. Okay, so number of successes, let's call it K. Okay, and K can be either 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11, 12, 13, 14, 15. Okay, so let's work out these probabilities. Boom, 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 boom. Well, you just plug in different values of K into this formula, and so I'll just tell you, what we get. Okay, so probability. Okay, so your chances of getting nothing correct, it's actually non-trivial. Okay, it's about 4%, approximately. These are now approximate numbers. The chances of you getting 1 correct is approximately 13%. 2 correct, 23%. 3 correct, 25%. 4 correct, 19%. 5 correct, 10%. 6 correct, 4%. 7 correct, 1.5%. 8 correct, 0.3%. Okay, and then basically approximately zero. Okay, this is about 10 to the minus 4, so this is about 0.07%. Okay, and then your chances of getting 10 correct are 0.01%, and 11 correct are 0.001%, and then 0.0001%, and then zero. I'm just gonna say 0. Okay. So let's look at this random test answering strategy. Okay. The most likely outcome is that you get 3 correct, 25% of the time. Okay. What about passing the exam? So if passing is defined as more than 50%, so then you need to get more than 7 correct. More than 7 correct is the sum of all of these. And the sum of all of these is approximately 0.4%. So 99.5, 99.6% chance of failing the exam if you answer it randomly. If it was 15 multiple choice questions with 5 answers per question. So don't answer these kinds of questions, randomly. It's not a good strategy. Okay, but now the important thing is to identify that, that's exactly the binomial random variable. Okay, and that shows you how commonly this type of experiment is occurring, and you're interested in the number of successes. Okay, and that just shows you, that we now have the tools to compute the probability of the number of successes. Okay, so now let's discuss the exponential random variable, or what's called the waiting time. Okay, so the waiting time. So it's a very similar experiment. It's basically the same experiment. Okay. The only difference, so you have a success probability. So you're trying something, and each time you try, you may either succeed or fail, and each trial is independent. So the conditions of this experiment are: you repeatedly try. So independent trials. Okay, and independent trials, and each trial has the same probability of success. Okay, so each trial has the same probability of success. Okay, so you try, you fail, you try, you fail, you try, you fail. We do this all the time on the internet. We try to send a packet, and if it succeeds, we're done. Okay, if it fails, we try again. If it succeeds, we're done. If it fails, we try again. Now, the chances of success when we try to send a packet are very, very high, 99.99%, okay, maybe. But there's still a small chance of failure, okay? Okay, so each trial has the same probability of success. Let's call it P. Okay. Now, what's the difference? Unlike the binomial random variable where you have a fixed number of trials, in the waiting time, there's no fixed number of trials. You just keep trying until you succeed. You just try, fail, try, fail, try, fail, try, succeed, done. Okay. So a lot of couples play this game with girls. You know, they keep trying until they have a girl. So that was Malik's game. You know, we kept boy, okay, boy, okay, boy. Then finally girls stop. Okay. So, you know, so this process, this experiment where you keep trying something until you succeed is very popular. Just like you keep trying something a fixed number of trials. Okay, it's a very common experiment that we all do in practice. Okay, in many scenarios. So let's analyze it. Okay, now what are we interested in? What's the measurement we're going to make for this experiment? The measurement we're going to make is how many trials did you make? Okay, so the random variable we're interested in is the number of trials to success. Or maybe I should say till success. Okay. So how many trials did you make until you succeeded? Okay. Now here, it's very convenient to just draw the outcome tree. Okay. So, you know, you start your experiment. Okay. And we played this, we did exactly this in the very first lecture when we said you keep tossing a coin until you get a heads. How many coin flips did you make? Okay. That's exactly the waiting time. The waiting time to the first head. Okay. Sometimes we might say I'm waiting till the second head. So you're having kids until you have your second girl. So then what's the waiting time till 2 girls? Okay. But here, you know, we're considering the most basic version of this experiment. You're waiting till the first success. Okay. And so I'll do it quickly. You know, you can either succeed on the first trial. So I'll do that as a success. Okay, so that's a success with probability P, or with probability 1 minus P, you fail. Okay, but then in the second trial, you might succeed with probability P, or you fail. Okay, or then in the third trial, 1, 2, 3, you might succeed, probability P, or you fail. Succeed or fail. Succeed or fail. And this could, in principle, go on forever. I mean, in practice, it'll always end. Okay, but in principle, it could go on for a very long time, even, you know. Okay, so each failure is 1 minus P, 1 minus P, 1 minus P, 1 minus P. Okay, and so this outcome has probability P. This outcome has probability 1 minus P times P. This outcome here has 1 minus P squared times P. This outcome 1 minus P cubed times P, 1 minus P to the 4th times P, and you get the pattern. Okay. Now, let's see this random variable we're interested in, which is the number of trials till success. What is X? Well, here it's 1, here it's 2 trials, here it's 3, here it's 4, here it's 5, and so on. And it's not going to take, you know, too much trouble to notice the pattern. Okay, well, the number of the probability to take K trials means you fail K minus 1 times, and then you succeed. Well, since each trial is independent, the probability of K minus 1 failures is 1 minus P raised to the power K minus 1, and then you succeed P, and that gives you K trials. Okay? So the probability of K trials to first success is exactly equal to P times 1 minus P to the K minus 1. And we very often like to write this as P over 1 minus P times 1 minus P to the K. So I just, you know, I divided by 1 minus P and multiplied by 1 minus P. And we often write this as beta times 1 minus P to the K, where beta is this guy, P over 1 minus P. Okay. And one of the advantages of writing it this way is that it becomes immediately obvious why we call this the exponential random variable. Because look, the probability that you have to wait K trials to the first success is exponentially decreasing in K. The probability of K trials is some constant, well, the constant happens to be P over 1 minus P, times 1 minus P to the K, exponential in K. Okay, and so this is why it's called the exponential random variable. Exponential in K. Okay, and that's it. That's the exponential random variable. Okay. So now we could compare the binomial and the exponential random variable. And I ask you to go and plot this. So pick a value of n. Okay, well, let's say n equals 20. And so, for example, p equals 1, let's say p equals, 1/4 or something. If you plot the PDF, if you plot this PDF, you'll see, just like what we saw here, there's a peak. Okay, so when n equals 15 and p equals 1/5, so n equals 15 and p equals 1/5, we see that the peak is at 3. So the possible values are 0, 1, 2, 3, up to 15. Okay, and the distribution is rising up to 3. So it's going up. And then it starts coming down. Okay, and basically hits 0. Okay, and if you take n large and p a constant, or p, let's say p not going to either 1 or 0, so as n becomes larger and larger, this approaches the very familiar, what you might be very familiar as the bell-shaped curve, or the bell curve, okay, which basically mathematically is what we call the Gaussian distribution. So this is approaches a typical bell-shaped distribution. If you look at this probability distribution function, so if I plotted it, okay, so the most likely choice, the most likely number of trials, okay, so beta is a constant. So this guy is decreasing with k. The chances that you have to make more and more trials is decreasing with k. So it's, it starts off somewhere, and then it starts dropping, and it drops very quickly to 0. Okay, and that's the exponential distribution. Okay, so let's do an example of the exponential distribution. Example. Very cute example. And this is going to show you again that, when we try to solve problems algorithmically, sometimes we cannot avoid using randomness. So this is now to seal the deal that certain things that we like to do, you cannot do them without randomness. And this experiment is going to come into play. This waiting time, this exponential distribution. So what's that experiment? There's a router. So there's a router. And you and let's say 3 other people, so Alice and Barb, are trying to access this router. Bam. So imagine time steps 1, 2, 3, 4, 5, and so on. If exactly one person tries to access the router gives you access, and you can communicate with the rest of the world. If more than one person tries to access the router at any given time, the router gets confused and it just says it blocks the access because it cannot service 2 requests at the same time. Okay, so simple strategy for you, Alice, and Barb. At every time step, you all try to access the router deterministically. So deterministically, everyone tries to access, okay, at every time step. Okay. And it's not just routers that face this issue, databases, database servers, when multiple people try to access. So the greedy thing to do is at every time step, who else is there in the world? Nobody else, just me. Let me try to access. So everybody tries to access. Fail. Okay. So what will happen here? What's called deadlock. Nobody will ever gain access to the router. Okay. So the only solution is what's called random backoff. Okay. Now, the actual protocols, the actual routing protocols that are in your Wi-Fi card and in the router do what's called random, not only random backoff, but random exponential backoff. So they do more sophisticated things. But the simplest thing you could do is say, you know what? It doesn't make sense for me to access at every time step because then, if someone else is doing the same thing, we're just going to clash all the time. So instead, let me randomly access. Let me decide randomly whether to access, let's say with probability 1/3. So everyone accesses with probability 1/3, okay, at each step. At each step. Okay, so now it is possible that all three people access at the same time, and then it's a failure. Okay, but let's see, what are your chances of success on any given step? So you access with probability 1/3, and you need the other two people not to access with probability 2/3, because so they're not going to be accessing with probability 2/3. So probability of you and not A and not B by independence. So we assume that each of you independently tosses a coin or a random number generator in order to decide whether to access, and you access with probability 1/3. So probability of you and not A and not B is equal to 1/3 times 2/3 times 2/3 equals 4/27. So that's your chances of success on a given trial. And you're going to keep trying to access this router, keep trying until you succeed. It's exactly this experiment. Okay. So let's see, what are your chances that you access on the first shot is 4/27. Okay. What are your chances that you have to wait for the second trial? Okay, it's exactly this experiment, and we can compute it. Okay, so we can compute beta is 4/27 divided by 1 minus 4/27. Okay, and so then we can compute, the probability. So K is 1, 2, 3, 4, 5, 6, 7, and so on. And what's your probability that you have to wait for one trial? So the probability that you have to wait for one trial is about 15%. There's about 15% chance that you will succeed on the first trial. Okay. The second trial, about 13%. The third trial, about 11%. The fourth trial, about 10%. Well, more like 9%. The fifth trial, about 8%. Okay, and the sixth trial, about 7%. The seventh trial, about 6%. The eighth trial, and so on. Okay. Approximately 50% chance that you won't have to wait more than 4 trials. Okay, which is reasonable. Okay, so which is not only reasonable, but it is way better than deterministic access by everyone, which is just complete deadlock. Okay, so this is an example where if we don't put randomness into the algorithm, there's no way for us to in any principled way avoid this deadlock. Okay, so you might say, everybody, instead of accessing at every time step, access every third time step. Okay. So Malik, your accessing time steps are 1, 4, 7, and so on. Alice, you are 2, 5, 8, and so on. Okay. Now you think that everyone gets 100% success, right? Okay. And they will be accessing 1 in every 3. So this is not much worse. You have to wait just for 4 trials, let's say typically. Okay. And if everyone were totally synchronized, we could get everyone accessing 1 in 3 trials. So this is pretty good. Okay, but now can someone tell me what is the problem with the, every third trial for Malik, and then offset by 1, every third trial for Alice, offset by 1, every third trial for Barb? Can someone tell me the problem? Okay, well, there are lots of problems. The first is, what if someone else comes in now? Okay, but let's assume someone else doesn't come in. The bigger problem is, well, what if we don't know when Alice is going to arrive to play this game? So what if Alice arrives to play this game on time step 3? So you told Alice you can't access on time step 3. You must wait, because that for Alice is time step 1. You must wait till time step 2, which is 4, which is exactly when Malik accesses. Okay, so having deterministic offsets is not going to work, because that requires people to be in some sense synchronized. They all agree on what time step 1 is. Okay, not easy to accomplish such synchronization in a distributed way. You have to take the distributed algorithms course if you want to learn how to do those kinds of things. Okay, so and even if you manage perfect synchronization, you only get to access every third try. And this random approach, which doesn't require any synchronization, gets access approximately every 4th or 5th try. So it's not much worse. So you don't even need to invest in synchronization. Randomness saves the day. That's probability at work when it comes to designing algorithms. Okay, so what did we discuss today? Today, we talked about the very practical, issue of you have complex experiments in practice, but we're not interested in complex outcomes. So we summarize the complex experiment into a random variable. Okay. The random variable summarizes the complex experiment into a measurement, and then what we're really, all we care about is what are the possible values for that measurement and their probabilities. And then once we have the PDF for the random variable, we don't really need to work with the complex outcome space for the experiment. We just work with the random variable. And then we talked about a lot of the random variables that are going to arise in practice: the Bernoulli, the uniform, the binomial, big ticket, and the waiting time, big ticket. Okay. So now, we're sort of positioned to go and analyze even more complex experiments. Okay. See you next time.